let's get started. Today it's our pleasure to welcome Arpan from the Harish Chandra Institute. He's been working on integrated detection of dark matter. Today he's going to tell us about early observations of the current and future of dark matter.
Thank you for the introduction. Thank you for inviting me here and giving me the opportunity to present my work. Today I will talk about the immediate search for dark matter in current and radio observation. As we all know, in 1933, astronomers Milky first realized that the mass of luminous matter in Gamma cluster was much smaller than the total mass, as implied by the motion of cluster member galaxies inside the system. So this was the first evidence of dark matter. Since then, there are several evidences, like the observation from the observation of galactic rotation curve, which shows that the stars inside the velocity, rotating velocity of the star inside the galaxy remain almost flat with the distance from the center instead of falling. So it's kind of explained by the existence of dark matter inside the galaxy, and also the observation of bullet cluster where two galaxy cluster collides with each other, and gravitational lensing effect shows that most of the invisible mass are in the outside region of the luminous center. Or one can also see the observation of anisotropy in CMB spectrum, which can be explained by the existence of dark matter. Today we know that 27% of our universe is made of dark matter, and its relative density is around 0.12 as measured by Planck. But till now, all these evidences of dark matter are only through gravitational interaction. So there are other detection procedures like delay detection, where dark matter particle comes in, collide with the detector nucleus, and goes out. One can measure the recoil energy of this nucleus. So this kind of experiment, like Xenon 1T and LARS, tries to measure this energy. And one can also look for missigity at the collider experiments, where two or more visible particles can produce associated with some invisible, associated with some unbalanced missing transverse momentum, which can be explained by the production of some invisible particles like dark matter. But no, till now, any direct signature of this of dark matter particle has not been found in this experiment. So one can also look for other kind of dark matter detection technique, which is called indirect detection. What is indirect detection? So inside some galaxy or galaxy cluster, dark matter can annihilate or decay, and this can produce standard model particles like quarks, electron, bosons, etc. These particles then further cascade and produce stable particles like photon, electron, positron, proton, antiproton, neutrino, etc. One can try to observe these stable particles like Fermi or CTA try to observe these photon or these gamma ray particles, or these antiparticle can be tried to observe in ALS2 experiment, and this ice cube try to observe the high energy neutrinos, etc. Here I will mostly focus on this electron positron production. This produced electron positron can emit synchrotron radiation as a result of cycloid motion under the galactic magnetic field. So in order to estimate this radio signal, one first need to know the amount of electron positron produced in the annihilation or decay. And this amount can be estimated by the so-called source function, which is for annihilation, and for decay is like this. So here sigma v or gamma is the annihilation rate or decay rate of the dark matter. This dNDE is the number of electron positron produced in one annihilation or one decay. This quantity, this BF, is the branching fraction or weighted to various standard model channels. And here the factor 2 is to account for the annihilation of two same dark matter particles. I mean, where the particle and antiparticles are same. If the particle and antiparticles are different, this factor will not be here. And finally, this quantity, this rho, is the dark matter density of the galaxy. The electron positron, after produced in the annihilation or decay, diffuses through the galactic medium, lose energy and give rise to equilibrium distribution, D and D. So this distribution can be obtained by solving this kind of transport equation, where the first term is due to the diffusion of the charged particle in the intergalactic medium, and this second term is due to the loss of the energy of the charged particle, and this Q is the source function which governs the rate at which the charged particle is being produced from the annihilation of the dark matter. So one can parameterize this decay term in diffusion terms dE in terms of diffusion coefficient D0 like this. So, and the BE, which is the energy loss term, encapsulates all the energy electromagnetic energy loss processes like inverse compound effect, synchrotron loss, etc. For example, for synchrotron loss, this term, this energy loss term BE goes as B square, where B is the galactic magnetic field. So, for this equation, this E0 and B enters through here and here, and so the solution will ultimately depend on these two parameters. So finally, once this electron positron is produced, they interact with the galactic magnetic field and radiate energy, and this is called synchrotron emission. The emissivity can be obtained by holding this equilibrium number density with the synchrotron power spectrum. So what is synchrotron power spectrum? It's the rate at which a charged particle with energy E radiate electromagnetic emission at frequency nu in the presence of a magnetic field B. So it is kind of averaged over all directions. So one need to fold this quantity with this and find the synchrotron emissivity. From there one can calculate the surface brightness and ultimately the integrated flux obtained from galaxy. So in order to predict the radio flux, one need to first, as we already seen, one need to first calculate this source function. So as you can see, the source function depends on the density of dark matter inside the galaxy. So in order to get enhanced flux, it is important to choose such objects as our target, which is expected to be dark matter dominated. So objects like dwarf spheroidal galaxies are good candidates for this. So these are mainly due to the reason that these dwarf galaxies are very near to us, which is almost within 100 kiloparsec. So they are also expected to have very high dark matter density, which is inferred from their high mass to light ratio. And due to the same reason, other astrophysical processes like star formation, etc., are well suppressed there. So we have less background in our process. So here I am showing the predicted radio flux from dark matter annihilation as a function of radio frequency. So for some dwarf galaxy like Draco, here we have assumed that the dark matter mass is around 80 scale and its annihilation rate is like this, and the dark dominant annihilation channel is BV bar. So this plot basically shows the variation of the predicted flux with these two parameters, this diffusion coefficient and B, magnetic field B. So one can see that the radio flux get suppressed if one increase the diffusion coefficient, and the radio flux also gets suppressed if one decrease the magnetic field. So these two parameters are very important to determine the radio flux, and as they are very important in determining the radio flux, one need to know this parameter very well for the dwarf galaxies. But unfortunately, these parameters are not very well constrained inside those local dwarf galaxies. Various theoretical arguments can predict that the magnetic field at those dwarf galaxy can be at the microgauss level, as has been explained in this paper. So one of this argument is like that the linear extension of the Milky Way magnetic field. So as these dwarf galaxies are very close, so they can have some part of our Milky Way magnetic field. So that can produce a microgauss level magnetic field inside them. So T0 is also very difficult to estimate. So it can be as low as 10 to the power 26 centimeters square per second, or it can be as high as 10 to the power 30 to 31 centimeters square per second. Sometimes people also work with this kind of value of diffusion coefficient, which is in analogy with the value of our Milky Way. We have used some benchmark values in those ranges or in those above ranges, but also try to scan the full astroparameter space. Now I will talk about the radio observation, the search for dark matter through radio observation in some upcoming radio telescope, which is Square Kilometre Array or SK. SK is the new upcoming radio telescope proposed to be built in Australia and South Africa. So it has large effective area, which helps to reduce its RMS noise level or threshold. For a generic formula for a radio telescope is like this, where this delta T is the observation hour, and this A effective is the effective or collective area of the telescope. So as SK has very large effective area, so its RMS level is very low. So in order to calculate this RMS noise level, one need to take into account the sky background, which is due to the CMB effect or the contribution from our Milky Way galaxy or the atmospheric effect. So taking all this into account, we find that the RMS sensitivity is around 10 to of SK is around 10 to the minus 6 to minus 7 Jansky over the frequency range 50 megahertz to 50 gigahertz for a few hundred hours of observation time. So as you can see, the frequency range of SK is huge. I mean, from megahertz to gigahertz. So it helps to this large frequency range and also this relatively high sensitivity makes it useful in exploring dark matter mass in a wide mass range, so, and even above a TU. So here I am showing the constraint in the dark matter annihilation rate versus dark matter mass plane for two different annihilation channels like BB bar and electronic channel like tau tau. This band is the escape detectability threshold for some dwarf galaxy like Draco for 100 hours of observation time. So and the band is due to the variation of the magnetic field from 0.1 to 1 microgauss. The choice of diffusion coefficient is like this, which is in analogy with our Milky Way belt. So, and this broken curve represent the upper limit in this plane from various other experiments. Like this dotted curve here are the limit obtained from observation of the gamma ray from dwarf galaxy made by Fermi. And this dashed curve is the limit due to the observation of cosmic ray antiproton observation by AMS. And we found that this is the most strongest limit in this case. And as you can see that not only for low dark matter mass like at the GeV scale, SK has potential to see very high dark matter mass model also, because for very high dark matter mass like EV or beyond, there are a significant amount of parameter space which is available for SK, or SK can probe this parameter space as well.
So this would offer the first band
variation of magnetic field point. This point 1 is here, and 1 micropulse is here. So if we increase the magnetic field, the radio flux get enhanced. So the limit gets stopped.
Do you have similar plots for TP bar and WW?
Yes. So the same conclusion for other channel like K-Boson or heavy core like TT bar. So here also there is a lot of parameter space available here, and the upper limit here of the corresponding cosmic ray bound. So let me now take some example from a very well-known supersymmetric dark matter model, which is minimal extension of standard model, or minimal supersymmetric extension of standard model, or MSSM. Here we have assumed that the lightest neutralino is the lightest SUSY particle and can serve as the stable dark matter carrier, and it covers the entire relic density observed by Planck. So here are some benchmarks taken from this paper. So I am not getting into the detail of the benchmark, just showing the corresponding annihilation rate, dark matter mass, and the annihilation channel for this benchmark. All these benchmark points satisfy the direct detection bound on stage from various collider search experiment, and most importantly, they produce relic density in the observed to sigma band. As you can see from the mass range of the neutralino, which is the lightest SUSY particle in our case, it is difficult to probe them in current collider experiment, even with high luminosity, or in direct search experiment. But in SK, one can try to probe them. So here again, the parameter space is dark matter annihilation rate versus mass. These upper bars are the corresponding upper limit at those masses for this kind of annihilation scenario obtained from the corresponding upper limit from antiproton observation made by AMS. Similarly, this lower bar represent the SK threshold for 100 hours observation at those dark matter masses for those kind of annihilation scenario. And these three are the three benchmark points. So one can see that even for very high mass, like at around 10 TeV, the SK is capable of detecting this parameter space very well. Now let me now point out some interesting fact about heavy dark matter. So the source function which I mentioned earlier, which enters into the transport equation and helps to estimate the final radio flux. So this source function is proportional to this factor sigma v by m chi square, where m chi is the dark matter mass. So as there is a m chi square suppression in the source function, so this suppression will remain in the final radio flux. One can expect that the radio flux will be suppressed for heavy dark matter mass, but that is not always the case. Let me explain why. So here I am taking the two of my three earlier benchmarks. So one is with dark matter mass around 1 TeV, and other is with dark matter mass around 8.5 TeV. Here I am listing this ratio sigma v by m pi square for these two benchmarks. So you can see that even though there is a 8.5 cross 8.5, that is 72-fold suppression due to the m chi square, this benchmark, the high mass benchmark, has larger sigma v, which helps to compensate the effect of this 1 by m chi square suppression, and brings the ratio sigma v by m chi square almost at the same level. This larger sigma v is needed for larger dark matter mass to satisfy the Rayleigh density. And one more important thing is the annihilation channels here. So both of them has BB bar dominated annihilation rather than other annihilation like tau. So how? So what is the effect of this annihilation channel? Let me briefly explain here. So here, this quantity is the number of electron positron produced in one annihilation in one pair of dark matter annihilation. So I am plotting this spectrum versus the energy of the electron for two different annihilation channels, BB bar and tau tau, and for two mass, which is around 100 G and one is around 1 G. So this red curve is for BB bar annihilation, the solid one for high mass, and the broken one is for low mass. So one can see that for BB bar annihilation, heavy dark matter has abundance of energetic electron positron in the spectrum. So what will happen that after energy loss in the galactic medium, this energetic electron positron will go to the low energy region and increase the equilibrium density D and D at low energy, which helps to produce larger radio signal. And also this abundance of energetic electron positron helps to offset the 1 by m pi square suppression. So together this effect one can get large radio flux for heavy dark matter mass. But for other annihilation channel, this effect is not very prominent. Like for tau tau, one has, for high dark matter, one has the larger amount of electron positron, energetic electron positron. But at low energy, this spectrum is suppressed for heavy dark matter. So this effect will work for this kind of channel like BB bar. And combining all this, one can get larger radio signal for heavy dark matter mass compared to low dark matter mass. Like I have shown here, one is for the model, this model, which is of dark matter mass around 8.5 TeV and one is around 1 TeV. But the high dark matter mass is giving larger radio signal over the entire frequency range, and this band is just the SK sensitivity for 10 to 100 hours. So the main reason for this enhancement of high dark matter mass is mainly larger annihilation rate, which is required for maintaining the Rayleigh density, presence of energetic electron positron in the annihilation spectrum in greater abundance coming from the heavy dark matter mass, which not only compensate the effect of 1 by m square suppression, but after energy loss enhance the equilibrium density DND at low energy, which further helps to produce large radio signal. And finally,
so that means if my dark matter is boosted by something, then you will have more.
Exactly. One needs to have this large amount of electron positron in your state. And finally, dominance of some particular channels like BB bar in the annihilation spectrum. So let me mention here that here MSSM has been just used for just for illustration. This phenomena holds true for other scenarios, other dark matter scenarios as well. One has to maintain just these three properties. So till now we were talking about the constraint on the dark matter parameter space using some approximation of these astrophysical parameters B and D. But one can go other way around, like using some independent knowledge of dark matter mass and annihilation rate. One can identify the viable region of this parameter space, this magnetic field and nu zero, using SK. So here I am showing one example of this. So this constraint on this plane is for some dwarf galaxy like Draco, and the dark matter mass is around the TeV scale, and the annihilation channels are like this, dV bar, tau tau. So what is this curve? So any point on this curve are the combination of BD0, which makes the radio signal detectable for SK for when the dark matter mass is around this scale, and the annihilation rate kept fixed at the upper limit obtained from cosmically antipolar observation. So if one have larger magnetic field or lower D0, that means for those combinations, the radio signal will be detected at SK even for lower annihilation rate than the upper limit set by cosmically antiproton observation. If SK is unable to detect any radio signal, that means it can rule out this much amount of parameter space, so which is up to very low range of magnetic field. So as of now, I was talking about only the annihilation.
For Milky Way, this B is kind of well.
For Milky Way, B is kind of well known. It is around 5 to 10 microgauss. Well,
So based on that, my prediction for dark matter signal is kind of.
But that's like in the center of the galaxy that feels like really measured practically.
For dwarf galaxy, as this parameter is not very well constrained, so we can try
There's two
to.
things here, like how do you, like what's the radial kind of, like you can measure the magnetic field at a certain sight line, like like how does that like get radial? That's where
Then you can.
well, so yeah, so this is kind of just a little bit of extrapolation.
For one problem for Milky Way is that for Milky Way, this parameter I think is very well constant. I mean the magnetic field or C0, but there can be some background for this radio emission. I mean, so there are many other sources than dark matter. So there will be huge background for this predicted radio flux. But for dwarf galaxies, that background is suppressed. But on the other hand, this parameter is not very well constant. So one can use this dark matter observation, I mean the predicted dark matter signal, to put constraint on these parameters like magnetic field inside the dwarf galaxy. So till now, I was talking about the annihilation of dark matter inside the galaxy, but one can also try to predict the radio signal which arises due to the decay of dark matter into standard model particles, and thus able to probe or constrain the decay parameter space. So in this scenario, dark matter is unstable, but its lifetime must exceed the age of the universe. So one important fact about decay is that the source function or finally the radio flux, which depends on this source function, goes as rho, which is the dark matter density of the galaxy, by dark matter mass, as opposed to rho square by m chi square, as in the case of annihilation. So there is a one order less separation of mass. So this can be helpful when one tries to look at heavy dark matter or the trans-TeV dark matter. So here I am showing that one can parameterize the decay of dark matter in terms of several dimension 6 operator, as has been shown in this paper. So this is just a small set of those dimension 6 operator. This phi 2, phi 1 here are two V2 or scalar particles in the dark sector. Phi 2 is assumed to be heavier and can serve as dark matter candidate. So basically phi 2 decays to phi 1 with two gauge bosons and two gauge bosons like to WW, to ZZ, or to photon, Z photon, etc. The mass difference of phi 2 and phi 1 is delta L. So we have assumed that one effective operator acts at a time, and if one operator is acting, then the corresponding interaction derived from this operator will be like this, where E and E prime are the gauge bosons. So this kind of operator will give you three body decay, like phi 2 goes to phi 1 and two gauge bosons. But one can parameterize the two body decay process as well with single component dark sector. And finally, this similar operator can be written for other sector of standard model like fermion and etc. So we have all done in this paper. So here I am just showing the for the gauge operator.
So okay, so here you're saying that phi 2 is a dark matter type. And then, but phi 1 is actually lighter than phi 2.
Yes, but the decay rate is so slow, and it's several order higher than the, less than the, the lifetime is several order higher than the universe lifetime, universe age. So one can assume that the inside those local dwarf galaxy or in some spaces there is still this dark matter is available because it is decaying so slow.
So okay, so you're saying so somehow you produce phi 2 in all universe exclusively as your cosmological dark matter, and then the later, late universe phi 2 decays into phi 1 and
Exactly.
Then the phi 1 is also could be dark matter.
Exactly. Phi 1 is also possible, but it will not decay. So decay signature will only come from phi 2.
But I guess you didn't think of the production mechanism of dark matter. Phi 2.
Yeah, we are not saying anything about that. We are just stabilizing the effective operator which is responsible for this kind of process and how one can constrain these effective operators through this indirect observation.
Okay, so somehow you also have to somehow the phi 2 multiplied in the dark matter sector.
Yes, yes. But there can be, fraction of phi 2 and fraction of phi 1 also possible. But that's just the linear scaling of the limit which I just showed.
But did you assume that phi 2 is just sort of the sum of dark matter or
Phi 2 is dark matter. Phi 2 is the decaying dark matter.
the thermal?
No, not. So here I am showing the constraint on the decay rate versus dark matter mass plane. This line here are the SK detectability threshold for this choice of astroparameter. Here the decay process is like a two body decay, phi goes to WWZZ, or a three body decay like phi 2 goes to phi 1 WW or phi 1 ZZ. This red curve here is for two body decay and this blue and green is for three body decay. So the blue and green are for due to the two types of mass difference between phi 2 and phi 1. One is when phi 2 and phi 1 has large mass difference. So in that case that will be similar to two body decay. But other kind of scenario when phi 2 phi 1 are very close, which is like degenerate scenario. So in that case, as phi 1 is very close to phi 2 mass, phi 1 mass is very close to phi 2 mass, the produced WW or produced ZZ, the other standard model particle, will be less energetic. So the electron positron produced in the cascade of this particle will be less energetic. So the radio flux emitted by those electron positron will be suppressed. So the limit is weaker for this case, as can be seen by comparing this green one with the blue one. Other thing is this magenta lines, these are the upper limit in this plane obtained from the isotropic gamma ray background observation made by Fermi-Lab. We found that this is the most strongest upper limit in our case. So one can also look for other gauge boson channel like the dark matter decaying to one Z and one gamma, or dark matter decaying to two photon directly. So for this channel you will not get any radio signal, so there will be no limit of, in this case. Here also one can get the limit, but one main difference in this case, in these two cases, is that the dark matter is directly decaying to a photon. So this for when the dark matter mass is very large, the emitted photon will be much energetic. For Fermi-Lab, which observe this photon, has a threshold at around 1 D. So beyond that it cannot measure very well. So Fermi-Lab limit is for up to this mass. So after that we have used the prediction made by CTA, which is going to be built for for observation of very high energetic gamma rays. So for CTA there is some limit, so one can use that. So other things are same as in the previous case. Now let me talk about the constraint in the on this effective coupling. I mean, the effective operators, my effective operators were like this. So one can put constraint on this effective coupling one by one. So this one is for this coupling and this one is for this coupling, and one can see that. So this blue one are the SK threshold for large mass difference, and for small mass difference, and for large mass difference, and these magenta lines are for the upper limit obtained from this Fermi-Lab observation. So one can see that here also for heavy dark matter mass like 10 TeV or beyond, there are significant amount of parameter space which are available, and SK can prove them with some moderate hours of observation time. And as in the case of annihilation, one can also try this for decay scenario as well. So using some independent knowledge of dark matter mass and its annihilation rate, one can try to identify the regions of parameter space, which is astrophysical parameter space, which is available for SK. If SK is unable to detect any signal, so that means it can rule out this much amount of parameter space. So one important point is that here the decay rate, the mass of dark matter is around this 10 TeV, and the corresponding decay rate or the effective couplings which determines the decay rate are kept fixed at the upper limit obtained from isotropic gamma ray observation made by Fermi-Lab. So in the final step of my talk, I will talk about the multi-frequency observation of Milky Way globular cluster. So globular cluster is a spherical collection of stars that orbit a galactic core. They are very tightly bound by gravity. Example of this kind of globular cluster in our Milky Way is like omega CA 47 Tucani, etc. So some globular cluster like omega CA is a good candidate for dark matter search like our dwarf galaxies, and the main reasons for this are that the high mass to light ratio of this kind of globular cluster suggests that it has very high dark matter content as high as our compact dwarf galaxies, and also this globular cluster is almost 10 times closer than our known local dwarf galaxies. So this reason can help to for loop omega towards omega string for dark matter search. So some recent analysis of Fermi-Lab data shows that there is a gamma ray signal from omega CN in the energy range few hundred MeV to few tens of GeV. One can explain this in terms of dark matter annihilation inside omega CN, as has been done in these two papers. So there are other possible astrophysical explanation also, like millisecond pulsar, etc. But they have their own drawbacks. So here I will try to here we assume that this gamma ray signal is arising from the dark matter annihilation, and if one assumes that, so one needs three quantities to explain this gamma ray emission. So one is the dark matter annihilation rate, dark matter annihilation channel, and dark matter mass. And also to estimate the amount of dark matter pair inside the omega CN, which is giving this annihilation, one need to calculate the astrophysical J factor, which is just the line of sight integration of dark matter density square. Some independent analysis of stellar kinematic data can help to determine this J factor, as well as the radius of dark matter density distribution inside this globular cluster, as has been done in this paper. So if one use this information about this J factor by fitting this gamma ray signal, one can find the best fit values of the annihilation rate and dark matter mass for some dark matter annihilation channel. So these two paper has done independently this fitting and obtained some values like this. So we use both of them in our calculation. So our main target is that, so what will be the interpretation of this kind of model which explains this gamma excess in terms of our radio observation. So recently Murchison Wide Field Array, or MWA, has done some radio observation towards omega CN. So MWA is one of the existing radio telescope located at Western Australia. Sensitivity is much weaker than SK, and its frequency range is around 200 megahertz. So during the observation of omega CN, MWA has to overcome the all kind of background or foregrounds in the direction of this globular cluster. One important object is called SEN A, which is a strong radio galaxy in the field of view or on the line of sight of this omega CN. So on the in the observation of this radio signal, one has to subtract the contribution from this kind of object and try to find the diffuse radio synchrotron emission associated with that omega CN. But in its first phase, MWA has not found any evidence of this excess diffuse radio emission. So using that and combining the search for gamma ray observation with this radio observation, one can constrain the astroparameter space, like here. So this is the constraint in the magnetic field versus diffusion coefficient plane. Using the dark matter model consistent with omega CN gamma ray observation, as has been done in these two papers. So this plot is for the dark matter model from this paper, and this plot is the dark matter model from this paper. So this shaded region is the parameter space which is ruled out by current MWA observation. Also the same story here. So one can see that it can rule out a significant amount of parameter space, this MWA. Here I'd like to mention that the estimation of magnetic field for omega c. So we found that it is around 1 microgauss to 10 microgauss, but by some independent estimation of magnetic field at the location of omega c. If we also use that in this plot, so we can see that this current radio observation can rule out the diffusion coefficient up to the value 10 to the power 27 centimeters square per second, or even larger than that, like 10 to the power 28 centimeters square per second. So this work has been done in collaboration with the NWA team. Like they are the. So with this, I'd like to conclude by saying that indirect search of dark matter through radio observation can play important role in dark matter phenomenology. The upcoming radio telescope Square Kilometre Array can observe dark matter induced radio signal for a wide range of dark matter mass, like from GeV scale to several TeV, and it is capable of constraining parameter space well beyond the reach of current collider experiments. Like we saw that it can constrain the parameter space for dark matter mass in the 10 TeV or in the range 10 TeV or beyond. So finally, combining the gamma ray or cosmic ray, this kind of experiment with radio observation, one can constrain the coupled parameter space of particle physics and galactic astrophysics. For example, using some existing data provided by MWA can already rule out some region in this parameter space. The SK is expected to provide much improvement in this.